Hello, I welcome you all to this another interesting screencast, and the problem reads, the shaft is supported by a journal bearing at A and a thrust bearing at B. Determine the normal force, shear force, and moment at the section passing through a point C, which is to the right of the bearing at A, and point D, which is just to the left of 3,000 pounds force. And I've also included a part where I'm saying draw the shear force diagram and the bending moment diagram. This problem is coming from the Engineering Mechanics and Statics textbook, 13th edition by Hibbeler. Right. So we have two supports, a journal bearing at A, okay, and this journal bearing allows this shaft to move in the horizontal direction. Therefore, we are going to only have one reaction force, which is just AY. While the thrust bearing, it resists both movements in the X and in the Y. So therefore, we are going to have BY and BX. Okay, we have this distributed force from C to D. Therefore, we are going to have an equivalent force, which will be acting at the midspan of so we have this distributed force. It will be acting here, midspan of the length of this rectangular distributed force. So it will be acting at 6 feet, and the magnitude of this or the equivalent force of this distributed force will be the length of this rectangular distributed load times the intensity, which gives us a 12 by 75, right? 12 by 75. Great. It's a 900 pounds. Great. So that is the equivalent force. So with that, then let's move on. Let's start working. What do we have? We have summation of moments about point B equal to 0 and clockwise being our reference. Let's start the work. So we have a 3,000 at point load. It will cause a positive moment by 2, and then we have a 900 that equivalent force by the lever arm, 6 plus 2, which is 8. And then we have a 2,500 by the lever arm, 6 plus 12, which is 18 plus 2, 20. And then finally AY by 12 plus 2, which is a 14, right? Okay, equal to 0. And therefore, our AY is going to be equal to, grab your calculator, 3,000 by 2, plus 900 by 8, plus 2,500 by 20. Okay, this one is negative, sorry. AY is giving us a clockwise. This one is a clockwise. This one is negative. Alright, and then divided by 14, which gives us a 4514 point. I'll write 4 decimal places. Okay, pounds. Let me just repeat this. 3,000 by 2 plus 900 by 8 That's 2500 by 20. Okay, divided by 14. Great. 45, 14.2857. Right. Then we have summation of forces in the y equal to 0, so that we find the other component. What do we have? We have a minus 2500 plus ay minus 900 plus by equal to 0. So we have minus 2500 plus ay minus 900 plus by. Great. I've forgotten another one. We have a 3000, right? Okay, let me include that one. It was almost hidden. Minus 900, and then we have minus 3000, and then we have plus by. Okay, great. So we've already found what ay is. So let's just replace ay. We replace it there. When we do so, therefore our by is just going to be equal to, we have minus 2500 minus 900 minus 3000 I come again, minus 2500 plus ay, which is a 4514, 45 14.2857 minus 900 and then minus 3000. Alright, therefore by is just 1885.7143 pounds. Great. And then we have finally the summation of forces in the x direction, that direction being a positive. Of course, we know that bx will just be equal to 0. Okay. So then let's start doing the sectioning. So we are going to do the section. We'll start at C, and they've told us again, it's very important to know which direction. Okay, they've told us for C, we are supposed to find the internal forces to the right of the bearing at A. So this is the right side, and this is the left hand side. So we are doing a section here. Okay, to the left, to the what? To the right of A. Okay, so let's draw. We are going to use the simpler section, so we're going to use the left hand section because it's much simpler, but we are doing it to the right of A, therefore the support will be included. Alright, so let's draw that quickly. So let's say it is something like this. So let's name this part here. We have A, B, C, D. So let's call this part E. Okay, so let's say this is our E here, this is our E, and this is our C. But at C, we are also including the support reaction A. Let me just write down this. We have AY, which is a 45 14.2857, and we have BY, which is 1885.7143, right? 43, great. And BX, we just said is equal to 0. So this value is included 45 14.2857. Okay, and then at the far end there we have this applied force of 2500. Great. Then at C we expect a VC, we expect MC, we also expect a normal force NC. The length of this section is 6 feet. Great. What else? That's about it. that is all the information. Okay, so let's start with applying the summation of moments about point C equal to 0 and clockwise being our reference. What do we have? We're going to have a 2500 by 6. Okay, and clockwise. What else? And then plus MC. Okay, plus MC equal to 0. Therefore, our MC is just going to be equal to minus 2500 by 6. It gives us a 15,000, okay, pounds. That's 15 kips, right? 15,000 pounds. And then we have summation of forces in the y equal to 0. What do we have? We have a minus 2,500, of course, minus. And then we have a plus 14.2857. And then we have a minus VC equal to 0. So minus, plus, minus. Therefore, our VC is just going to be equal to minus 2,500 plus 45 plus 4514 4514.2857 4514. Okay, then therefore this gives us a 2014.2857, okay, pounds, which is a positive shear. And then we have finally summation of forces in the x direction. What do we have? Of course, the normal force is just going to be 0 pounds. So we have finished with one part. Let's move on to the other part. Let me just create some space here like so. Okay, so we'll make another section. We're going to make a section at D. D, we've been told it is to the left of 3000. Okay, to the left, so it will be there. Okay, to the left, so we have the right, we have the left, to the left, sorry, to the left it is here. Okay, yes, so we have the left hand section, we have the right hand section. We are going to go with the right hand section because it's simpler. Okay, go for simple things. Right, so there we go. Let's indicate everything that we have. We have a D there, we have a B here, a B here, and then here we have the support. The support here is 1885.7143, and then this will be included, okay, which is a 3000 because we've been told to the left of this. And of course here we expect the VD, and then we'll have MD, and then we have ND. Okay, and the length here is just equal to 2 feet. Okay, let's start the work. So we'll have summation of moments about point D equal to 0 and clockwise being our reference. What do we have? We have 1885.7143 times the lever arm. This is giving us anti-clockwise. Then minus MD equal to 0. And therefore our MD is just going to be equal to 18 1885.7143, right? 1885.7143 times 2. So this gives us a 3771.4286 pounds feet. Okay, this one is pound feet. Okay, pounds feet. That's the moment, right? Okay, 4286. Okay, great. Then we apply the summation of forces in the y equal to 0. What do we have? We have a plus VD, a minus 3000, and a plus 1885.7143 equal to 0. Therefore, our VD is just going to be equal to minus 3000 plus 1885.7143, 1885.7143. So this gives us a 14.2857 pounds, and that is going to be a positive shear. And then finally we have summation of forces in the x direction equal to 0. Of course, we know that our ND is just going to be equal to 0 pounds because we do not have any active force applied in that direction. Right, so we found everything that the question was initially asking for. We have the moment MC, which is negative. We have shear, which is positive, and we have the normal force, which is a 0. At D, we have the moment, which is positive. We have shear, which is positive. Of course, we have the normal force, which is equal to 0. So like I indicated, we are going to draw the shear force and the bending moment diagram. So we are using the equations at the rate of change of moment with respect to x is equal to shear, and the magnitude of the moment is just the area under the shear force diagram, and the rate of change of shear with respect to x is equal to a distributed force, and therefore shear is just equal to the area under the load diagram. So let's prepare our line work so that we begin drawing this quickly. There we go. We have got that one there, that line work, and also we've got this one there. Great. And this is going to be equal to our shear force diagram, and this is bending moment diagram. And we have positive up, negative down, positive up, negative down. Great. Okay. These are just markers to indicate where change is going to be taking place. Great. So quickly, let's start. Our initial value at E for shear, we have a negative value of 2500. Let's say it is coming up to there. So this value, let's say, is a 2500 pounds. And then we know that from E to C, we don't have anything. Q is equal to 0, which is the distributed force from E to C. And because it's 0, we expect the slope of our shear diagram to be 0. Okay. So 0 just means a straight line up to here. And then when we arrive here, the two are going to interact. So we'll have a negative 2500 plus 45 14.2857. So this gives us we have a minus 2500 plus 45 14.2857. So we have a 2014.2857. So we're going to have a positive value. So shear will move up to a positive value of about 2014. Let's say it is somewhere there. So this value is 2014. Let's indicate it there as a 2014.2857 pounds. And then from C to D, Q is just negative and constant, and therefore you expect V prime, which is dVdx, to be equal to negative also and constant. And this value is area under the load diagram, which is just equal to minus 75 times the length of our load, which is 12. Okay, and this gives us a 900, right? We had already calculated it. Okay, 900, a minus 900, that we shouldn't forget. This is a minus 900. Okay, so the two interact. Will have a 2014.2857 minus 900. So what does this give us? So a 2014.2857 minus 900. So this gives us a positive 1114.2857. Okay, so let's draw. So our slope will be constant and negative. So the negative constant slope. So this is going to drop to about that point. Let's say that is our 11. So that point there is 11. Let me just clean up this part, and we can also clean up part of this. All right, so this point here we are saying is a 1114.2857 pounds. All right, then from that point there we have that point load of 3000 negative, so we'll have 1114.2857 minus 3000. So the two will give us, so have 1114.2857 minus 3000. So this will give us 1885.7143, and this is a negative. Okay, let me write it again. Is a negative, so it's minus 1885.7143. Okay, great. So our shear will drop to that value. So from here we expect a drop up to somewhere there. Let's say that is our 18, somewhere there. Okay, maybe we put it somewhere there. That is our 18. Let's say this is our 18. This is going to be our 1885.7143. Again, you don't have to maintain for decimal places. 2 is enough. And then from D to B, of course, Q is equal to 0. Therefore, V prime will be 0. So it's just a straight line. So from there, it's just a straight line. Let me use my color. It's a straight line from there. And then when it reaches where we have a B, of course, these are the similar values you've seen. So these, they'll add up algebraically. One is positive, the other one is negative. Therefore, it will give us a 0. Is that fine? Of course, it's supposed to be fine. Okay. So I think this is about it. This is about it for shear. So we have a negative there. Let me get black. We have a negative there. We have a positive there, and we have negative there. Great. So let's draw the bending moment diagram quickly. Let me just clean my slate. I clean my slate. Great. So maybe I move this just a little bit down. Is it fine? Just down, just a little bit. Maybe up to there, like so. Okay, great. So from for the moment, from E to C, the shear is negative and constant. Okay, and therefore our M prime dm dx will also be negative and constant. Okay, and the magnitude of our moment is the area under the shear diagram, which is just equal to minus 2500 times the length, which is 6, and that gives us 2500 by 6 gives us a minus 1500, 15,000. Okay, at E we don't have any initial value of shear, of moment. Therefore, we expect moment to be 0 at E, and it will have a slope which is negative and constant. So negative and constant, we expect this to come up to there like so. Let's say that is the value that we are getting of 15,000 pounds. 15,000 pounds. Then from there onwards, we have V, which is positive and it is decreasing. Therefore, M prime will also be just equal to shear. M prime will be positive as well as decreasing. And the magnitude is just the area under the shear diagram. In that case, we have a trapezoid. So let's find the area of the trapezoid. So it will be 2014.2857 plus my space is not enough, so let me just use red. M is equal to 2014.2857 plus 1114.2857 times half times the length, which is 12. Okay, so this gives us, let's work out the area for the trapezoid. 2014.2857 plus 1114.2857. We sum up the 2 times half times 0.5, which is half, then times 12. So we have the moment of 1877.4284. Is that 4? Okay, let me redo it. 2014.2857 plus 1114.2857 times half times 12. The length is 12, right? So 18771.4284. Great. So then the two interact. We have a minus 15,000 plus 18771.4284 equals to, so this minus 15,000, so we get a 3771.4284. All right, so it will move from here. It will have a positive value. Okay, each slope is positive and decreasing. So this is going to be a polynomial of degree 2. So we are moving from this point from E to from E from this is where we are from E to C. We've done that. This is now from we were here. Let me write down here. That is from C to D. Okay, that is what we are doing. All right. So this destination is at this destination is at D. Okay, so the slope, like we've been told, is positive, but it is decreasing, and this is going to be quadratic. So we expect something like this. What's the value? 3000. Okay, something like that. Great. This is 3000. 3771. Let me write it properly. Okay, 3771.4284 pounds feet. This is pounds feet. These are the units, pounds feet. Also here there is feet. All right. Then finally, which is the closing part. So what do we have? From D to B, we have shear, which is negative and constant, and M prime will also be negative and constant, and therefore magnitude of our moment is just area under the shear diagram, which in our case is just a minus 1885.7143 by the length, which is a 2. So let's find out what we have. 1885.7143 by 2. We have a 3771.4286, and this is negative. Okay, this is 1885.71 by 2. Okay, so when the two subtract, when we have the two subtract 3771.4284 minus 3771.4284.86. Okay, we just expect a 0 point. It's just 0. Okay, it's just 0. So you expect this is going to be equal to, so you have 3771.4284 minus 3771.4286. So this is a 0.00, a negative, okay, 0.002, right? 1 2 3 4. Okay, which is just basically equal to 0, right? Which is just going basically equal to 0. All right, so and this will close up at this point here. We're going to have a closure because when they subtract, they are giving us a 0. So let's close up this, and this is negative, the slope and constant. So this is just going to be like this there. Let's bring it where it's supposed to be. Let's say up to there like this. All right, and I think this is about it. This is really about it. Let's check what we have found and compare with our diagram to see whether it makes sense. So we have MC. Where is it? Just here. we are talking of shear to the right of A, and shear to the right of A was a 2014, right? And it's fine. Shear differs, okay. If you are cutting, you're finding shear at a point where you have a concentrated load, then it is going to be different to the left and to the right. But when you just have a space like this, M1 shear is the same, just like shear from this part to there in between this region it will be. It is going to be varying, right? It's going to be varying. Okay, but here shear is the same, okay, in that region. So it's really important to follow these steps. And then we had moment at C. Moment at C there is the same whether on the left or on the right, and we found a negative. So this is negative, we had forgotten to indicate, and this is positive. And the normal force was 0. And what was this is D. And then for MD we are talking of shear to the left of 3000 to the left, okay. We found shear of 1114.28, yes. And moment at C, we found a 3771.4286. Okay, so where did I miss out on doing the multiplication? Let me just check again. 2857 plus 11.2857 times 0.5. I'm just working out the area for the trapezoid, times 12. Okay, and then minus 15,000. Alright, it's giving me that. Anyways, they are just still okay. They are just close to each other. The difference is very minor. Okay. So this is the final solution. And I hope the video was helpful. And if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.